So hello, everybody. I'm very, very glad to have the chance to talk to you. I've not given this talk before. It all started around 18 months ago when I wrote down a little equation you will see, and I actually wrote it down on a napkin. So my colleagues and I affectionately call it the Napkin Equation. I'll give it a more pretentious title in a moment. So I hope I can do this reasonably well. There's a lot of text that I've written because there's a lot of history and facts that I just don't know so well otherwise. So can you go to the next slide, please, Alfredo? So this is the shape of history, and my collaborators are written above: Roger Koppel, Ricard Soleil, Sergio Valverde, Jordi Piñerte, Jim Harriet, Abigail Devereaux, and Wim Hordick. Part of this work is on archive at the link that's up there, and you guys have this, so if you want to read it, you can. And the title is A Simple Combinatorial Model for Economic History, and it's been submitted for publication about a couple of weeks ago. Can I have the next slide, please? The long evolution, so we're starting, strangely enough, we're going to start 2.6 million years ago. So the long evolution of stone tools from the lower Paleolithic, 2.6 million years ago, I presume you remember Australopithecus, then Homo habilis evolved, then Homo erectus, and then to Homo sapiens in about 100,000 years ago in the Neolithic. So we're really going back 2.6 million years. Can I have the next slide, please? This is a picture of an actual stone tool made by a girl who was an Australopithecus 2.6 million years ago. Our ancestors, before there were modern humans, started making stone tools, and this is one. It's kind of a hammer digger. And it was found next to her body 2.6 million years ago. Next slide. So this is Homo sapiens. This is Cro-Magnon. See the pressure flaked stone tools? They're beautifully flaked, and this is around 40,000 years ago. Next slide. So these are about 14,000 years old, and it's Neolithic artifacts, including bracelets, axe heads, well, you could read it, polishing tools, and so on. Look how much humanity has advanced. But notice that it is taken from 2.6 million years ago to 50,000 years ago to get this far. Notice also that the diversity of tools is increasing, and you can start to see that there's some more complex and some less complex tools. That's going to be fundamental to what we're talking about. Next slide. So I'm going to be talking about hockey sticks. So this is a hockey stick. And the basic idea is that it goes along and then suddenly shoots upward. Major hockey sticks in human history. Human culture, so I have to read all of this, everybody, so just please put up with it. Human cultural evolution is replete with long periods of glacial advance, followed by quite sudden rapid increases, or hockey sticks, in world history over the past 2.6 million years, since the lower Paleolithic with Australopithecus, then Homo habilis, then Homo erectus. The growth of the number of tools and goods, and their differentiation into simple and increasingly complex tools over eons, is a hockey stick, since its glacial pace for hundreds of thousands of years in the lower Paleolithic, followed by the upper Paleolithic and Mesolithic, then the arrival of Homo sapiens about 100,000 years ago, and the Neolithic 70,000 to 15,000 years ago, to its explosion in the last few centuries. World gross domestic product, GDP, and per capita GDP followed the same glacial advance for some 500,000 years, then burst upward since 1700 AD. So urbanization was glacial for thousands of years, then burst upward in the same past 2 centuries. Architecture, from caves 500,000 years ago, to huts, to multifamily compounds in the Neolithic, to the World Trade Towers. Governing scale over 500,000 years. Bands of 8 to 15 people as hunter-gatherers, to clans of several bands, to chiefdoms, to tribes, to early empires 5,000 to 4,000 years ago, to nations, and now to the UN. This too is a hockey stick over 500,000 years. So too our music and the evolution of the diversity of instruments over thousands of years. This is amazing. 50,000 years ago, Neanderthal had drums and bone flutes. We've had flutes for 50,000 years. To lutes, lyres, and cymbals in Mesopotamia, to medieval Europe, to the 20th century crescendo in the number and diversity of instruments. The hockey stick slow growth followed by the explosion of science since Mesopotamian and Ptolemaic astronomy to Newton to today. And most critically, the hockey stick explosion of human culture itself. There's hockey sticks all over. Next slide, please. I'm going to make 3 propositions about human behavior, and almost everything I'm going to say, except one thing that I'll tell you much later, follows directly from this. The most important is the following. Since Australopithecus, we take whatever we have and recombine them in many possible ways, and we accumulate what works. That's going to become the napkin, or I'll call it the theory of the adjacent possible equation in a moment. The Wegener-Fechner law, discovered in around 1870, we perceive stimuli, such as how loud a noise is, proportionally, hence logarithmically, to their intensity. And third, the effectiveness of a human group is proportional to its size. That just constant returns to scale in economics. Next slide. The theory of the adjacent possible, TAP equation, capturing the fact that we combine whatever we have and accumulate what works. I'm very proud of this little equation. I wrote it down about 18 months ago. I was wondering, given that there's M goods in the economy now at time T, can I write down an equation of some kind for how many goods will be in the economy at the next period, say a year later, at MT plus 1? So here's what it says. MT plus 1 is equal to MT. That's what we've accumulated from the past, plus the new things that we can make by recombining things, which is the last big term on the right. That's some probability P, which might be 0.2, times a sum of a running index I running from 1 to MT. So if MT is 10, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then alpha I is a little, it's an important parameter in the equation. It says roughly it's easier to jury rig one thing out of one thing. It's a little bit harder if you try to do it with a pair of things, a little bit harder if you try to do it with 3 things, a little bit harder if you try to do it with 4 things. And the last symbol is MT, choose I. So that just says is MT is 10 and I is 2. It's choose all possible pairs of things out of MT. So right below that, you can see MT choose I is equal to MT factorial divided by I factorial times MT minus 1 factorial. So just to be concrete about it, if I is 2 and MT is 10, it's 10 factorial, 10 times 9 times 8 times 7 times 6, times 2 factorial times 8 factorial. That just gives you the total number of goods in the economy, and M at time T is the total number of goods in the economy, M at time T. The theory of the adjacent possible equation is mathematically a known equation. It's called the exponential integral equation that my colleagues and I are exploring. The 2 main parameters are M0, the initial number of goods, and P, which pretty much sets the time scale to the hockey stick explosion in the increasing number of goods in the economy that I think you'll see on the next slide. Can I have the next slide, please?
Yes.
So there's 4 figures below, well, 3. Figure XX below shows world gross domestic product for the past 2,000 years, which is startling hockey stick initiating about 1800. Figure XXX below shows the theory of the adjacent possible predicted time course of world GDP compared to real world GDP for the last 2,000 years. In fact, we've done it for the past 20,000 years. I just don't have a good slide of it. And figure XXXX below shows the TAP predicted time course of world GDP since 1800 compared to the true time course. So I hope you will agree that the theory fits real world data closely. Depends on the choice of the mathematical parameters, of course. Next slide. So here's world GDP for the last 2 millennia. And you can see it's essentially at 0. It's very, very small in units of trillions 2,000 years ago. This stretches back to Australopithecus. World GDP was incredibly low for hundreds of thousands of years. And then it shoots up, as you can see, starting around 1850 with the Industrial Revolution, and it's shooting upward now. Next slide. So the green line that you see there is world GDP, and the other colored lines are the fits of the theory of the adjacent possible equation to it. So the theory of the adjacent possible has the remarkable property that it goes along very, very low for a very long time, then suddenly shoots upward in a hockey stick. We don't know any other equation that does it. It may be the case that there are other equations to do it. This is not linear in a log-log plot. This is not a power law. It's something else, and it's captured by the theory of the adjacent possible equation that I showed you. Next slide. So this is from 1800. I guess the blue line is real GDP since 1800, and those are the fits of the model to it. We needed to take more time points to make the curve a little less jagged in the theory, but you can see that it fits it quite well. Next slide. Tentative conclusion. The proposition that we keep whatever works and recombine what we have in many ways, which is expressed by the theory of the adjacent possible equation, seems to capture something fundamental about how we humans have evolved with respect to tools, goods. We'll see social organization. Since Australopithecus started making stone tools 2.6 million years ago. The reason to start with Australopithecus is Australopithecus really did start making tools that gradually became more complex over millions of years, and then hundreds of thousands of years, then 10,000 years. And now we've gone from Australopithecus to a space station. Next slide. So I want to talk about, you all know what per capita GDP is. It's the gross domestic product per person. It remained essentially constant for thousands of years at about $300 per year. That's subsistence level until about 1500 AD. It's kind of astonishing, but the bet is that Cro-Magnon was living about as well off as people were in the year 400 in the south of France at about $300 a year. Since about 1500 AD, world per capita GDP began to increase slowly, then in a hockey stick upwards in the past 2 centuries. The figure below will show the logarithm of per capita GDP from 1500 onward. Now, to use the theory of the adjacent possible and obtain a prediction about the glacial then rapid increase of per capita GDP, just divide the TAP predictions over time by the population size over time, just using population data. Thus, at each time t, divide the TAP predicted GDP by population size at time t to get predicted hockey stick growth of per capita GDP over time. Next slide. So this is time from 1500 to 2000, and the vertical axis is the logarithm of per capita GDP. And what I want you to really pick up, because we're going to need this in a minute, is that it really starts going up a little bit after 1800. And by 1900, it's zipping upward. I mean, look at that curve. Next slide. The theory of the adjacent possible predicts that for thousands of years, GDP itself does not grow. TAP predicted per capita GDP, i.e. GDP divided by population, is obviously smaller than GDP itself, and essentially it's constant given a stable population. This has really big implications. For many thousands of years, as TAP predicts, and in real life, as population may have slowly grown, it ran into a constant GDP, and hence an essentially constant per capita GDP, in a Malthusian world of subsistence living, with perhaps short bursts of population growth, when the stable per capita GDP then enforced less than subsistence per capita income of perhaps 300 a year. The population then died back to a stable population level over perhaps 100,000 years, more than that, it's over 1 million years. This is the vast bulk of humanity's economic history. Here's the crux of it. When GDP and per capita GDP started to grow in 1700, then ever more rapidly, here's the crux point. Its pace of growth became faster than population growth. So GDP and per capita GDP is growing more rapidly than the population is growing. So the population could explode exponentially upward in what's called the Great Transition. That means that a few hundred years ago, human population exploded. Next slide. So here's human population for the past 10,000 years. And you can see it shoots upward at around 1800, 1700. So that's world population. And this is huge. This is a human history. And the theory of the adjacent possible with a long glacial period when not much happens, then shooting upward, I think predicts it. It fundamentally explains it. At first, it's very hard to make new kinds of things. And then after a while, the TAP equation says that you can make new things more readily. And that's fitting the GDP. Next slide. So I want to talk about urbanization over thousands of years. There were no cities in the Paleolithic. In the Neolithic, settlements with small and larger, quotes, hums evolved in the beginnings of inequality, discussed in the figure below. By the Bronze Age, 5,000 to 4,000 years ago, the Indus Valley, the Hittites, the Mesopotamians with Ur, and Egypt all saw both cities and empires. Almost their entire population lived rurally, farming in the several thousand-year-old agricultural revolution that brought surplus wealth and patterns of inheritance that both bred increasing hierarchy and the emergence of power elites. Extensive urbanization has only increased in the past 150 years. For example, in the United States, only about 4% of the populations lived in cities in 1800. About 70% of the US population lives in cities now. Next slide. So this is a picture of artifacts from the Bronze Age. And let's just stop and think about it for a moment. This is the Bronze Age. There's a human skull on it. There's what looks like some pots. I don't know what the metal things are. Maybe they're swords. But in the Bronze Age, you had a distribution. I really want to get this idea across. The first needle was found about 50,000 years ago. It was a bone needle. In the Bronze Age, you have a larger, much larger number of goods than Homo Sapiens had, than Cro-Magnon had. And there's a range of goods from very simple, such as needles, to very complex things like chariots with warriors in them running around. So there's an enlarging number of goods and an enlarging distribution of these into simpler and more complex goods. Next slide. This is urban area, this is urbanization over the last 10,000 years. And you see that it shoots up starting around, as it turns out, 1800. There's a little bit from the time of Christ on. For example, there's the Roman Empire. Next slide. Very good data show that the extent or fraction of the total population living in a city is proportional to the logarithm of per capita GDP. You'll see the figure. I'd like very much to get this across. This is likely understandable based on the Wegener-Fechner law that we perceive stimulus differences as differences in a ratio of stimuli. It's on a logarithmic scale, not a linear scale. So per capita GDP approximate wages in the city, urban wage, call that WU. A per capita GDP of 0 approximates very low rural wages. Thus, WU, urban wages minus rural wages, approximates per capita GDP. So the extent of urbanization, 0% to 100%, scales as the logarithm of per capita GDP. Next slide. So this is data from 1500 to now. On the x-axis is logarithm of per capita GDP, and on the y-axis is the extent of urbanization from 0% to 100%. It's convincingly a straight line with hundreds and there's 2,217 observations, and it's convincingly a straight line. Notice it does not go through the origin. It doesn't start until there's a substantial per capita GDP. I think we explain this by the Weber-Fechner law. It's really true that we perceive things logarithmically. Just for example, when I looked up, it's also called just noticeable differences. People who do marketing, when they want to try to sell you a box of cornflakes with less cornflakes in it so they can make more money, but you won't notice it, use exactly this principle. Next slide. So I've just showed, this is entirely true. The figure shows the extent of urbanization scales as log per capita GDP even today. Figure X below shows per capita GDP over time in the UK. It begins to rise in around 1850. Urbanization parallels this time course in a hockey stick. It really parallels log per capita GDP. And then figure XX below shows the time evolution of urbanization in terms of the largest and mean city over time. So this theory of the adjacent possible predicts the hockey stick of urbanization from predicted log per capita GDP over evolution over time plus Weber-Fechner. It's expected, this is just astonishing, that the majority of humans will live in cities in about 50 years. Next slide. Go back one. So this is GDP per capita in England since 1270. And per capita GDP is starting to rise pretty clearly in around 1800. If you take the logarithm of that, you just lower it, you just lower the y-axis to make log GDP. And you'll get the same hockey stick a little bit more sharply, really going up at around 1850. Next slide. This is time. Don't look at the biggest, the top line. That's the biggest city, and that includes the Roman Empire and a bunch of other things. Look at the dark line, which is the mean size of cities, and you see that it starts shooting up at around 1825 to 1850 to 1875 to 1900 to 1950. Urbanization has happened in the last 200 years. Why? Okay, next slide. So I want to remind you what a logarithm looks like. So this is just y is equal to the logarithm of x. So I think you can't see the numbers, but the first number on the x-axis is 1. Log of 1 is 0. If you take the log of a fraction, it's a negative number. What I want you to look at is the right-hand part of the curve, where the logarithm of x, y is equal to x, is positive. And just notice that the curve has a second derivative that's negative. It's getting flatter and flatter and flatter. The steepest part of the logarithm curve is just above 1. It's going up more steeply, and then the further that you go out to the right, the more gradually it goes up. Namely, the tangent to the curve is steepest at 1, at x equals 1, and it gets less and less and less. This is going to be central, so please keep it in mind. Next slide. One of the puzzles is urbanization in the second and the third world and in ancient civilizations. And what I now want to tell you is this predicted by the theory of the adjacent possible plus Weber-Fechner. So we're going to use that the percent of urbanization is K log per capita GDP and Weber-Fechner to explain megacities in the second and third world. One of the puzzles is that in the last 30 or 40 years, huge cities with 10 million people in them have come up in the second and third world, like Manila in the Philippines and Kinshasa or whatever it is in the Congo. There's a very large number. It's now estimated that the megacities in the world will mostly grow in the second and the third world, not New York and not London. The question is why? And the answer is, I think, so just picture that logarithmic curve that we just saw. The first dollar means more to you on a logarithmic basis than the last dollar. So a relatively small increase in per capita GDP is a big increase in log per capita GDP because of the logarithmic curve. And therefore, I think we explain getting megacities in countries that are still quite poor, like the Congo. I want to use the same thing to explain urbanization, ancient empires. Why did we get empires 5,000 years ago? The Indus Valley, the Hittites, the Egyptians, Mesopotamia. Increased GDP 10,000 to 4,000 years ago, and per capita GDP came with the advent of agriculture, the resulting growing extent of landholding. With the invention of the plow, you could really farm. So a growing surplus of wealth in land, in harvest, and domesticated animals, and inheritance. We're going to see evidence for this well before the Bronze Age. We're going to see it in the Neolithic. So I think we explain the emergence of the empires 5,000 years ago by a combination of the theory of the adjacent possible, which says somewhere around then you were beginning to get not only the agricultural revolution, but complex goods like we saw, including chariots and knitting needles and wheels and pots. Next slide. Turning to a new topic on the evolution over time of the distribution, not only the number of goods, but the distribution of less and increasingly complex and valuable tools, therefore goods, therefore of wealth inequality and power hierarchies from the Paleolithic and Neolithic to now. So I'm turning to a whole new topic and trying to use the theory of the adjacent possible to explain the gradual evolution not only of more goods, but their differentiation to simple and complex goods. Again, in the Bronze Age, you had simple goods like needles and pots, and you had complex goods like chariots. Now we have simple goods like needles and space stations. In the lower Paleolithic, some 2.6 million years ago, Australopithecus had only a few roughly hewn stone tools of low and similar low complexity. For example, unifacial stone scrapers are an example, and we saw a 2.6 million year old stone digger when we started. Over thousands of Paleolithic years, the lengths of stone knives crept from 2 centimeters to 10 centimeters. It took hundreds of thousands of years, or certainly 100,000 years in the lower Paleolithic. Small hunter-gatherer bands were essentially of equal, very low wealth. Next slide. They didn't have very much to be unequally wealthy about. By the mid-Neolithic, wealth inequality and even transgenerational inheritance was in place. Typical Neolithic sites exhibit a dispersion of house sizes from small to large, hence the presence of inequality. Tim Kohler has just looked at about 67 Neolithic sites and looked at inequality in a way that I'll define for you in a moment, and it's clearly present. I find this amazing. Excavation of one Neolithic site discovered a number of rudimentary graves and 3 with buried children wearing jewelry comprised of hundreds or thousands of shells strung on strands. The shells came from hundreds of miles away. So this is around 40,000 years ago. These archaeological Neolithic findings demonstrate surplus wealth, social inequality, probably power inequality, and maybe most important, the transgenerational inheritance that allows the elites to pass their wealth to their offspring down the generations, thereby preserving inequality, wealth, and power. The Gini index, we'll hear a lot about it, measures inequality. It is 0 if there is full equality across society and 1 if maximally unequal. The Gini index of Neolithic sites ranged from 0.05 to 0.17. Next slide. By the time of modern Homo Sapiens, Cro-Magnon, 30,000 to 14,000 years ago, so please let me convey this clearly. The number of sophisticated pressure flakes tools had increased a lot, and there was an increasing diversity of complexity, had grown from very few tools in the Paleolithic's bone needles to several hundred tools ranging from simple to increasingly complex items, such as ancient bone needles and simple stone spear points, and the use of flax thread, to more complex fluted fishhooks and even more complex handheld compound spear throwers and even stone huts. So a compound spear thrower, which has some name, is an extension of your forearm. You hold a stick at the far end of which there's a pocket that holds the base of the spear, and you could throw it very much faster velocity. It's sort of like a lacrosse stick, and it was one of the most complex things that Cro-Magnon had. That's a complex thing, and I just want you to compare a stone hut and the compound spear in their complexity with a needle. They're already beginning to be a differentiation into simple and complex goods. Next slide. By the Bronze Age, we've already said this, Hittites, Mesopotamians, and Egyptians, thousands of tools and artifacts were in place, ranging from musical instruments such as flutes, drums, and cymbals to simple pottery and spears up to far more complex and highly valuable chariots pulled by horses for warriors, and a dispersion of house sizes from simple to very large. Social stratification was high, from the lowest poorest to the emperor. The spatial extent of government control was huge. The same was true of Aztec civilizations. In the 21st century, the number and increasing diversity and complexity and value of goods has grown from perhaps a dozen rudimentary stone tools of similar low complexity in the Paleolithic to billions of goods today, ranging in complexity from modern needles for sewing to television to computers to cell phones to aircraft carriers and the space station. Next slide. I think we've already seen this, so just keep going. So this is the space station. These are two Russian cosmonauts on the space station. One of the things that I find astonishing is the Wright brothers invented the airplane in 1903. By 1969, we were on the moon. Look at the rapid pace that Homo Sapiens has advanced. That's 66 years to get from the airplane to the moon. Cro-Magnon was as smart as we. It took 10,000 years to get from Cro-Magnon 15,000 years ago to the Mesopotamian civilization in the Bronze Age. Why is it going so fast now? Well, the theory of the adjacent possible, I think, explains it. It's that as you build and accumulate more things that work, there are more and more and more ways that you could recombine them to make still more new good things and more complex things, and the whole thing explodes, and that's what the equation does. Next slide. This is sort of a summary. The shape of history, the evolution of human culture is the story of a gradual, then more rapid increase in the number and growing differentiation of the complexities and values of goods, artifacts, agriculture, musical instruments, growing inequality, the emergence of elites with patterns of inheritance, growing surplus wealth, even before the agricultural revolution with its requisite holding of land, to today, with vastly many goods of highly diverse complexity, governmental range, and the stable inequality of the British aristocratic system over centuries and the power elites of today. I'm going to try to use the theory of the adjacent possible to find a framework in which to position this shape of history. Next slide. So I'm now going to reinterpret the equation we started with above, which was mt plus 1 is equal to mt plus that complex things about ways to recombine things to make new things by a recombination process. So this is redeploying the theory of the adjacent possible to analyze the growing number and also the growing distribution of simple to ever increasing complexity and value of goods over time since the Paleolithic. So here it is. Let MT, for period T, MT, be the most complex good innovated in the economy at time T. For example, MT stands for the number of parts in the most complex good first created at time T. Or perhaps it's the number of goods, of parts, M, at time T, times K, the richness of coupling between the parts. For K roughly constants, the complexity of goods coming into the economy for the first time is proportional to MT. It's proportional to MT. So MT is scaling how complex things are when they come into the economy. And the fundamental intuition is you can't make the next more complex thing until you make the slightly less complex things. You couldn't make a searchlight for ships at sea until somebody had made a good lantern. Once you had a good lantern and a mirror, you could try to make a searchlight. We were just watching Connections by James Burke. It's an amazing story of this since about 4,000 years ago with the invention of the plow. Next slide. The economy at time T then has goods, please understand this, simultaneously. It's a distribution of complexities and values from simple to complex. And the theory gives the simplest good is M0, the next simplest good is M1, the next more complex good is M1, the next more complex good is M2, to the current final period, MT. So that's going to give us a distribution of complexities of good because M at time T stays small and then gradually shoots upward. This grows by the time T plus 1 when a new good is improved of yet higher complexity and value, which is not often early in the theory of the adjacent possible, but as tap takeoff occurs, new and more complex goods, MT, arise in each period as the hockey stick takeoff arises and increases over time. Next slide. So this is my attempt to show this, and I thank my wife, Catherine, for drawing this. There are 4 panels here: Paleolithic, Neolithic, Bronze Age, and 2000. There are lines in each, black, blue, green, and red. The length of the line is roughly the number of goods at that time. So you can see the number of goods is going up in this sketch from Paleolithic to 2000. And the curvature on the y-axis represents complexity. So in the Neolithic, there's very few tools, and they're all of very low complexity. By the Neolithic, there's just the hint of slightly more complex tools. There's more tools, and the slightly more complex tools include stone huts and the spear thrower. By the Bronze Age, there's a lot more goods, ranging from the needle to the chariot. And for us, there are goods ranging, the billions of goods we have that we've already said, ranging from the sewing needle to the space station. Next slide. This redeployment of the theory of the adjacent possible, where MT becomes the most complex good produced at time T's, allows TAP to hope to predict the differentiation over time of a set of goods into simple and ever more complex and valuable goods. And with this wealth inequality and the emergence of social and power hierarchies, TAP implies that over time the distribution grows with an ever-increasing number of goods, of ever-increasing differentiation into simpler and ever more complex goods. Next slide. The appearance of a new good and more complex and valuable good per TAP is very slow initially, matching the slow increase in complexity and diversity in the Paleolithic. For example, knife blades longer over thousands of years is a measure of advance in the complexity of stone tools. By the above, from the Paleolithic for thousands of years, the number of goods increased in time very slowly, and the differentiation to less and more complex was very slow because initially MT increases very slowly. Next slide. Care must be taken using the Gini index for the Paleolithic and Neolithic due to Taleb showed the following thing. There's a high standard deviation of the Gini index for small group size. If the group size is 1,000, the standard deviation is 6%, and that 6% is a huge change but anyway, using the Gini index, the hunter-gatherer clans was essentially 0. Remember, 0 is essentially equality. There was nothing to be unequal about 70,000 years ago. We didn't have very much. We were just bands hunting around in the wilderness, out in the forest where we were in the jungle. And it was hard to be unequal because we didn't have anything to be unequal about. There was no surplus. There was no differentiation to simple and more complex, simple and more valuable objects. In early Neolithic sites, as I told you, Gini is 0.05 to 0.15, showing the onset of inequality and heritable hierarchy. Gini for late Neolithic sites is 0.2. There's clear signs of wealth inequality, inheritance of wealth, and power hierarchies. The Gini index in the United States is now 0.545, and it's growing rapidly, paralleling high and rapidly growing inequality of wealth and power in the first world today. Next slide. Social and power hierarchies. By Weber and Fechner, and data that the extent of urbanization is proportional to the logarithm of per capita GDP, this is just a bet. It seems reasonable that the degree of hierarchy in a society is roughly proportional to the logarithm of maximum complexity of goods, hence total wealth, or GDP, hence inequality in the society. Wealth and inequality obviously grow over time. This says that wealth and inequality scale roughly with power, and power scale roughly with the growing distribution of simple and ever more complex and valuable goods over time. An example is the English hierarchy and aristocracy for centuries. There's viscounts, then above them are lords, then earls, then marquis, then duke, then prince to king. That doesn't even count commoners. Not counting commoners, this is 7 orders of magnitude of roughly exponential increasing wealth and power. And if you imagine that a commoner has 10,000 pounds and go up by an order of magnitude to the viscount, lord, earl, marquis, duke to prince and king, it looks roughly right. It means the king has something like 100 billion pounds. And we have people in our society right now who have $100 billion, or on the order of $100 billion. So that's happening. Our wealthy elites are also correlated with high political power. It has been the same tap source of inequality from the Neolithic onward. Next slide. Turning to a new subject, it's the last subject. How are we doing on time? We're doing pretty well. Yeah. The growing populations, as well as wealth and power inequality in our growing cities in the last few centuries. Next slide. So we're going to start with something called Gibran's law, and which you probably don't know, and Zipf's law, which you probably do. Gibran's law, which is an empirical law, it's just an empirical observation, is that the population of a city grows exponentially proportional to its size. So bigger cities are growing faster than little cities, just exponentially. It's true across many cities. The question is why? So I've made three propositions about people at the beginning that we rearrange and tinker with what we've got and accumulate what works. Weber-Fechner law, and that the effectiveness of a human population is proportional to size. Here's the last fourth one. When urbanization, population inflow to a city occurs, it is proportional to the current population of that city. So let me read it again. Urbanization, population inflow to a city is proportional to its current population, and essentially no new cities are formed. It's true that the dominant growth of cities is in fact due to urbanization and the inflow of population. This is the supply theory of city population growth. The proposition above implies that cities grow proportional to their current population. But this is Gibran's law. So we've deduced Gibran's law by the proposition that urban inflow to a city is proportional to its current population. I don't think there's anything terribly bright about this. Other people have advanced the same idea in trying to understand and derive Gibran's law. Next slide. By Gibran's law and the proposition above, the predicted mysterious slope of relative city size in a country is, of course, -1, because cities grow proportional to their population. So if you plot different cities, the slope on a log-log plot is going to be -1. This will soon become Zipf's law. Now we make use of the effectiveness of population size n scales with n. This is constant returns to scale. Thus, city, not population, but GDP, grows exponentially proportional to n. This implies that I should have given you slides to see this. Jeffrey West has written a book called Scale, which is just a superb book. I've got it right next to me. Gosh, who published it? I'll let you know. Anyway, it's the universal laws of life, growth and death in organisms, cities, and companies. So he also talks, it's a wonderful book. Anyway, West shows the following thing. If you take the logarithm of GDP and the log wages, they scale with log city size. The slope isn't 1, it's a little bit more than 1, 1.15. It's superlinear. And West did a wonderful body of work to show that the endpoint, the slope of 1.15 scaling, is due to social networks in cities that have a fractal dimensionality of 1.15. It's lovely work. So we get out of this also that the total wages in a city, which is something like KGDP of the city, scales linearly with log total wages, scales linearly with log population size. And the figures are in West's book. Next slide. Gibran's law can be used to derive the zip distribution of relative city sizes. So if you just go online and say derive Zipf's law from Gibran's law, different people derive Zipf's law in a variety of ways, some of which are a little more intuitively clear than others, but it's clear that you could derive Zipf's law from Gibran's laws. Zipf's law gives the power law slope -1. No, let me say something about this now. We've gotten from my propositions about people essentially to Gibran's law itself by the proposition that people coming in from the rural areas go to cities proportional to their size. And fundamentally, we're pretty close to deducing Zipf. Zipf gives the power law slope -1 relation between city rank, where the largest city is rank 1 and population. So this is a relationship between the, I haven't said this very clearly. The Zipf law is a relationship between city rank, where the largest city is rank 1, and population. It's a power law slope of -1. So New York is rank 1, LA is rank 2, Chicago is rank 3. New York's normalized population is 1. What's astonishing is that since LA is rank 2, its population is predicted to be 1/2 that of New York, and it is. Chicago, with rank 3, is predicted to have a population 1/3 of New York, and it does. So on to rank X, where the population is 1/X times New York. And it's true. Zipf's law holds in the US and most countries. I'll show you a figure in a minute. It turns out that if the variance of city growth is positively or negatively correlated with city size, the Pareto slope for ranked city size is different for 1.0, which is true for some, but not too many countries. Next slide, please. So this was done done a few years ago. This is 135 of the largest US metropolitan areas in 1901. And it's data, and it was put together in 1993 by, it might have been by Paul Romer, I can't remember. Anyway, it's log of rank on the y-axis and log of population on the x-axis. And it's a very convincing straight line. And the slope is in fact -1, but you can't tell from this graph. So it's astonishing to me that Zipf's law holds. It holds in most countries, and the slope changes a little bit if the variance of city growth rates is correlated with city size. Next slide. So I want now to turn to something that's going to tell us about measures of inequality, the Gini index. This Gini index is on the y-axis, and how it correlates with the population in a city. So the x-axis is the logarithm of the population of a large number of cities, and they've drawn by linear regression a straight line through the data. Well, there's obviously a lot of variance, but you can convince yourself that this is really correlated with the logarithm of population, because if you imagine stretching out the x-axis so it was linear in population size, this data would smear way out to the right. So I'm going to continue to use this. I do have a slide that I find just astonishing that I'm not showing you. It's a slide that shows people's satisfaction with their life, and their satisfaction with their life scales as the logarithm of per capita GDP. So I think all these things go together. Next slide, please. The Gini index, as we now know, is an accepted measure of inequality. Again, a Gini of 0 is complete equality, a Gini of 1 is maximum inequality. So we've just seen from the slide that I show you that with some scattered noise, the Gini index of inequality scales linearly with a logarithm of population size. This is really important. Big cities like New York are much more unequal in the distribution of wealth than small cities like Sacramento. And it's true. Next slide. Next slide. By Gibran's law, proportionally smaller cities grow so I'm now going to try to turn to the following. We've already concluded that big cities are more unequal than little cities, and New York has a lot more inequality in it than a small town in Nebraska. I now want to try to talk about the way the Gini law changes over time, and I think we can derive it. By Gibran's laws, proportionally smaller cities grow exponentially, proportionally more slowly. Given the Zipf's law distribution of city population sizes, the exponential growth rate of a city of rank X should, absent other factors, be E raised to the 1/X power. So New York should grow proportionally at E raised to the T. I should put in there raised to the, time is not in there. Well, it comes into the next one. But Chicago should grow 1/3 as fast because it's third rank and it's 1/3. And LA should grow as 1/2 or 1/2. And Sacramento should grow at something like 1/400 T. Since the exponential growth rate of the population of city rank X is E to the 1/X times T power, I finally got T in time, the logarithm of the growing population of a city over time is just 1/X. And if we want to do it over time, I should put back in the T. Thus, the Gini index of a city of rank X should grow linearly in time, at the rate 1 over x. That means that small and large cities grow ever more unequal in their growing inequality. So New York's Gini index is growing linearly in time faster than the Gini index for Sacramento. So already New York is more unequal than Sacramento, and 10 years from now, the inequality is going to be even worse because of this. Next slide. Thus, for small cities, inequality measured by the Gini index increases slowly and linearly over time. For large cities, inequality measured by the Gini index increases rapidly and linearly over time. So in New Zealand, the exponential growth rate of the population has been stable, and the Gini index, as proportion to the logarithm of population size, has in fact grown roughly linear since 1920. See the figure below. It's a little noisy, but it's essentially linear. So I'm going to tell you some data that I just found yesterday, and I emailed it to Alfredo just before I talked. I haven't had time to make a slide of it, but just notice that what's going on is inequality is going up linearly with time. The Gini index is going up linearly with, same thing's true in the United States. So I don't have the slides to show you this, but what we've just said is that big cities are more unequal than little cities, and inequality is getting worse linearly over time. I just found a slide in a fantastic book I am reading called The Great Leveler by Seidel of inequality over the last 10,000 years. There's data from Italy and Holland in around 1500 or 1600, no, 1500. So it's roughly 1400 and 1500. It's roughly the Renaissance. And what it shows is that from 1500 to 1800, in Holland and in Italy, the Gini index does in fact increase very convincingly linearly over time, from very high Gini indexes of around 50 to around 80. There was high inequality in Italian cities and in Dutch cities when the Dutch flowered in all of their wealth in the 1700s. And it increases linearly over time. And the other thing that the book, The Great Leveler, makes clear is that in 1500, there was a difference in the inequality in which big cities like Florence were far more unequal than little cities in Tuscany. What this tells us is the present inequality that's growing ever worse between New York and Sacramento, and it's getting worse, was there 500 years ago before the invention of capitalism. I find this fascinating because people are trying to explain, as you will see, what's happened to inequality in the first world in the last 150 years with the invention of capitalism, but there's something more fundamental going on. And it may be the case that the theory of the adjacent possible is the fundamental explanation. After all, what's happened since the Paleolithic is we've invented more goods and an increasing dispersion of simple and complex, hence more valuable goods, from needles to chariots. A chariot is more valuable than a needle, and that gives us something to be unequal about. You have to have something to be unequal about. You can't be unequal about things when it's 50,000 years ago and a band of 18 of us is wandering in the forest looking for some game. So I think that the theory of the adjacent possible is the foundational idea that allows inequality to grow. Next slide. Gee, I'm doing pretty well in terms of time. So there has been considerable concern about inequality in the first world. In 1955, an economist named Kuznets theorized that in early industrialization, inequality would increase, basically because you're just disrupting the workforce. So they're coming in from rural areas and they're going into factories, which is very different. But that as development advanced to later industrialization, institutional factors such as labor unions demanding higher wages and transfer taxes from the richer to the poorer would narrow inequality. Kuznets was right. In the United States from about 1870 to 1920, inequality increased sharply. From 1920 to 1975, inequality fell and a strong middle class grew. Well, why? First of all, there were strong labor unions in 1975 and in 1950, and there was a highly progressive income tax. When I was young, my father was in the 90% bracket. So the last dollar that he earned, he kept 10 cents. He didn't like it very much, but that transferred a lot of wealth from the rich to the poor. The other point that Seidel makes in The Great Leveler is World War II caused a great compression in inequality, so that in Japan, the wealthiest 1% owned a much larger fraction of the total assets of the country than they did after the war. It was a fantastic leveling. So there have been these great compressions over time, but we're talking about from 1875 or 1870 to now. The kicker is the following. Kuznets could not have foreseen the fact that from 1975 to now, inequality has increased dramatically. So we're going to see two figures next. The last one is due to my colleague Pietro Nero. Okay, so this comes from Pareto distributions. It's the beta index. It's the beta coefficient. High means unequal and low means more equal. So you can see that in 1910 and 1920, across a bunch of English-speaking countries, United States, Canada, New Zealand, United Kingdom, and Australia, inequality is very high in 1915 and 1920. And it goes down and down and down, and it reaches a low in 1975. But it's shooting up again between 1975 and now. Fundamentally, nobody knows why. I'll tell you what people think. Next slide. Yeah, so Pietro Nero did a wonderful analysis. He's an Italian physicist working on economics. The vertical axis is not the Gini index. It's a University of Texas measure of inequality in the society. And GDP per capita is on the y-axis. So this is in the year 2000 or something like that, or 1990 to 2008. So it's not across time. What Pietro Nero did is take countries that are early in industrialization on the left, as measured by per capita GDP, that are later industrialization, measured by per capita GDP, and you see that in the green band from the left side, inequality is going up. Then as per capita GDP goes up further, in more industrialized countries like for example, Holland or whatever it is, inequality goes down, and then on the far right, it's starting to go up again. I guess he stops in 2008. So what this says is Kuznets was right. Something about World War II, labor unions and a progressive tax flattened the inequality, but it's going up again. And the question is why? Next slide. Growing inequality in recent decades, particularly in large cities, is now a major social, political, and human issue. Inequality measured by Gini or the Pareto distribution is now rapidly increasing in many nations and large cities, threatening social cohesion, deep loss of trust, and increasing anger. Inequality seems to be an inherent part of economic growth and a present danger. It's driven by the juggernaut of human creativity itself. I'm going to use this as a springboard to tell you a little bit about a man named Thomas Piketty. He is a French economist who a few years ago published a book that sold about 1.5 million copies called Capitalism and Inequality or something like that. Here's the rudiments of Piketty's idea. I only basically understand it. He roughly says, take wealth and divide it into income and capital. He then points out that income, namely wages, the growth of wages is roughly proportional to the growth of GDP. And it's been going up at about 2% a year. And that's roughly right. If you look at wages and per capita GDP, their ratio stays close to kind of 1 or 2. On the other hand, he says, the return to capital investment is around 5 to 6%. And he's right. Capital investment means you put money into your factory and you buy equipment that'll last 40 years. That's capital investment. And the return on capital for the last 250 years, says Piketty, and he's done the analysis, is 5%. Well, he then says, but if you're earning 5%, you can take the return and reinvest the capital and get more return. So the wealthy get wealthier and the workers don't get very much wealthier. So inequality is going to go up over time. He may have the right explanation for why inequality is going up. It ties into the theory of the adjacent possible, because the latter theory tells us that over time you create goods of ever increasing complexity, So as I've now said several times, in the United States, we have needles and we have the space station. And the space station is a lot more valuable than needles. So you can make a lot more money, you can be a lot more unequal, and you can invest your capital in capital investment in things that will be highly valuable because there's highly valuable things to invest in. So inequality is going up. And I mean by juggernaut that the juggernaut that is captured by the theory of the adjacent possible, which starts off glacially slow, then explodes in the number and complexity of goods, is human creativity itself. Since Australopithecus started fiddling around with rocks 2.6 million years ago. Next slide. So we're near the end. 2.6 million years ago, Australopithecus utilized the process of recombining what lay at hand and accumulating whatever worked. The equation expressing the theory of the adjacent possible seems to capture this broad process of technological evolution, even of cultural evolution itself, as in music, architecture, basket weaving, science. The theory of the adjacent possible yields a way of understanding both the emergence of ever new goods and technologies, but also over evolutionary time, the forming of a spectrum of less complex to more complex and valuable goods. The next more complex good can only arise out of the complexity that already exists. You couldn't make the space station since we'd gone into space. There is no way to leap from the Paleolithic to the Bronze Age. This vast cumulative evolutionary process over eons and more lately over centuries builds both increasing wealth, GDP and per capita GDP, but also increasing wealth and power inequality. Well, I've now said this many times, but I hope the ideas are clear. Next slide. Lessons from history. In this fine recent book, The Great Leveler that I've told you about, it witnesses the repeated, I can't read the word here, the repeated something of families, of societies, I think it's collapse or failure of societies for 10,000 years. As increasing wealth inequality bred revolutions, collapse and otherwise. For example, in China, in 2000 BC, there's a succession of empires from the Han to some of the others. And what happens is growing inequality increases, and then that period collapses, and a new ruler comes in. Social cohesion and trust among the people of a nation all decrease as inequality blossoms, as it does now. We are in danger from the very juggernaut of human creativity driving this increase in inequality. And this is what is striking me so hard, perhaps beyond our capacity to cope, captured in the theory of the adjacent possible. I mean, maybe labor unions and progressive taxes won't do it anymore. Maybe they will. The same theory of the adjacent possible tells us that now, 2,600,000 years later, following the hockey stick industrial revolution, the very same rushing juggernaut of human creativity is overwhelming the planet with global warming, acidification of the oceans, waves of species extinction events in what is now the Anthropocene. See the figure below. These are vast issues on a global scale that we Homo sapiens must now confront as one species. We're one species on the blue dot planet. Next slide. This just shows you qualitatively from the New Scientist, the Anthropocene, and there are, I can't read it, but there's things like global warming and increasing numbers of species extinction events in chemistry, chemicals in the atmosphere, and fisheries dying off and so on. And it captures the idea that we are encroaching on our planet, hell-bent on overrunning the only planet that we have. I find this very disturbing. I can imagine some things like carbon taxes and turning to solar and wind for energy, helping with global warming, and building seawalls, helping with the rising ocean. I don't see what we're doing helping with respects to the Anthropocene of rocketing extinction events and diseases coming out of the woods as we like Ebola coming at us out of the as we encroach on the habitats of creatures. I don't know how we're going to solve it. So we've got this growing inequality, which is bad, and we've got the impact on the planet that we really have to confront. Thank you.
Thank you.